So what we have right now is we want to find out the currents and the voltages going across the different resistors that we have. So what we see is that we have we have two parallel circuits here. We know that because they're going around and the current can go through one or the other. However, because the currents come together and have to go through the 8 ohm resistor, we know that one's in series. So the series resistor is connected to the parallel ones. Now we want to find the total resistance. Now total resistance, that means that we're going to say that all of these together have a resistance. Now to find parallel, you're going to add up the reciprocals. Now doing that, we know that that's 1 over 12 ohms plus 1 over 6 ohms. Okay? So knowing that, we can then add those up. We get 3 over 12, or 1/4, which means that the parallel resistor is 4 ohms. However, we still need to add the series. So the series is going to add the other 8 ohms, and that will give us 12. So that's our equivalent resistance of everything together. But the question is, what is the current passing through each bulb? Well, to start, we need to know the current that's coming out of the battery. So since we know that it's 6 volts and 12 ohms for the whole thing, then we're going to divide them, because current is voltage divided by resistance. Also, voltage is equal to current times resistance, by the way. Now, as we do this, the current is going to be 6 divided by 12, which is 0.5 amps. Now, remember we saw is that things that are in series are going to have the same current. So it turns out that the series resistor is also 0.5 amps. Now, we can't know how to split it between the other two resistors. So what we're going to do is we're going to start off finding voltages. Now we know that the voltage is current times resistance. So the voltage across this 8 ohm resistor is 4 volts. Now we know we had 6 to begin with, and now we've used 4 down here. That leaves us with 2 across the parallel resistors. However, what we learned from previously is that parallel circuits don't split their voltage. They both keep the same voltage, like so. So we know that those are the voltages going across each one. Now to find the current, we're going to divide. So it turns out that our 12 ohm resistor has 1/6 amps of current because of 2 divided by 12, and the other one is 1/3 because of 2. So now what we see then is we've got the current across each one, and we've got the voltage across each one. So B and C are both completed. Now rank the bulbs from brightest to dimmest. Okay. So what we want to see then is it's important to note how much voltage is across each one of these resistors, each one of these light. Now it turns out that when you are actually trying to find the brightness, brightness is related to power. Now it turns out that power is equal to the voltage times the current. Now we'll talk about this again tomorrow, but if you increase either the voltage or the current of a light bulb, you'll end up increasing the power, and that determines on if it's bright or not. Now, what we want to note, okay, is that if we want to find the power across each one of them. Now, power is going to be in watts, by the way. So let's go ahead and use current times voltage. So for the 8 ohm resistor, that's going to be 2 watts of power. Then if we had the 12 ohm resistor, that's 1/3 watts. And then if we have the 6 ohm resistor, that's going to be 2/3 watts. Okay, so it turns out that the 12 ohm resistor is the dimmest. Then we have the 6 ohm resistor, that's the dimmest, that's the next dimmest, and then the 8 ohm is going to be the brightest. Okay, so this is in brightness. All right, so just take the voltage times the current, and you can determine the brightness because that's the power. Okay? Now, suppose the switch in the circuit at the right is closed. So, in other words, there is a connection here. Okay? What effect does this have on? Okay, so what we're saying is we started off with just these two here. Now, once we get through that, we're going to get one that goes through here. Okay? So, how does that end up changing the voltage across the light bulb AB? Okay, so let's start off by figuring out what they would be already. So notice that our first two were in parallel. Okay, so 1 over R is 1 over 6 plus 1 over 6, which is 1 over 3. So therefore, the total resistance was 3 ohms. That means 6 volts divided by 3 ohms is going to give us a current of 2 amps. Okay? Now, that 6 volts was going to be across both of those light bulbs, because they're in parallel. Now that being said, that means that each one of them had 1 amp of power. Sorry, 1 amp of current. Okay, so we've got all those so far. Now with all of this, okay, we had. Now we could say, okay, what about the power? Well, the power for each one of those, that's going to be 6 watts and 6 watts. Okay, so that's what we had when we were starting. Now, what we're saying is, what happens to the delta V across light bulb AB? Well, let's say that we went back and we redid all of this. So now our new resistance is going to be 1 over 6 plus 1 over 6 plus 1 over 6, which gives us 1/2. So the new resistance would be 2 ohms for the total. Okay. Now that being said, we know that now instead of so instead of 2 ohms, what would be, sorry, instead of 3 ohms, we're saying 2 ohms, which means the current would be. So now that we know that the new current is coming off of it, now let's look at how this affects our voltages. Okay. Now, we know that since we have 6 volts, it's going to be 6 volts across everything. Okay. So we know that we've got 6 volts, and now 6 volts. So with that being said, though, now we know the current is going to be 1 amp for this new one as well, which means its power is also 6 watts. So it turns out the current in the first 2 bulbs is actually going to end up staying the same. Okay, that's because we just ended up increasing the current by decreasing the resistance, which means that it all balances out. Now, the current through point G. Okay. By the way, and the voltage across light bulb AB, that stayed the same as well. Now the current through point G, however, it ended up increasing. Okay. Increased from 2 amps to 3 amps. Okay. Now with that, okay, the power dissipated by the first 2 bulbs should end up staying the same. Now, here's the idea. Let's go back over why this is the case. When you had your voltage, you knew that there was 3 ohms of resistance, and you ended up finding the current was 2 amps. And that's fine. Then you were able to use those 2 amps and identify that they're going to go across 1 amp for each of those 2 resistors, and they both had 6 volts. Now, each one ends up 6 watts of power, and that's fine. However, notice that now when we connect the new resistor, what changes is the total resistance is now 2 ohms instead of 3. We have now lowered the resistance, which means we increased the current. Now that's good because we need that current to go through our third resistor. So it turns out that all 3 of them will have 6 volts because they're in parallel. And it turns out that all 3 of them are going to have 1 amp each because we've split up the current among the third one. But that also means that the power is going to stay the same for the first 2 light bulbs. Now notice, when it was only 2 light bulbs, that was only 12 watts of power. However, now it's 18 watts of power. So even though this seems like a great idea, that we now have 3 light bulbs and they all have the same brightness as what they had before, The thing is, though, that it's going to take more power and it's going to end up costing you more. So that's the downside, is that it will cost more to keep all three of those light bulbs running. Now let's say a 10 ohm and a 15 ohm bulb are connected in parallel and placed across the terminals of a 15 volt battery. Okay, so let's draw the circuit diagram. So we have a 10 ohm and a 15 ohm bulb, and they're connected in parallel and placed across a 15 volt battery. So that's our circuit diagram right there. Nothing too complicated. That's positive, that's negative, but that's normally the big one is positive anyway. Now calculate the equivalent resistance. So we know 1 over 10 plus 1 over 15 is going to be, so that's 3 and 2. So that's 5 over 30, which is 1 over 6. Okay, so we've, make sure, 3, 2, okay, good, awesome. So then therefore the equivalent resistance is the reciprocal, which is 6 ohms. Now note that, by the way, since that's 6 ohms, then we know that the current going through the entire circuit is going to be 15 volts divided by 6 ohms, which is 2.5 amps. So it turns out we have 2.5 amps right there. Now calculate the current in each bulb. Well, since we know they're in parallel, we know that's 15 volts and 15 volts. What that means, though, is that when we're calculating it, it's 1 amp and 1.5 amps. Okay, which makes a total of 2.5, by the way. Now, let's say we calculate the total power delivered by the battery. Well, remember, power, that's going to be voltage times current. So this one's 15 watts, and this one's going to be 22.5 watts. So it turns out that your total is going to be 37.5 watts. That's, oh, sorry, that's, I should put it down here, 37.5 watts. That was just by multiplying voltage and current for both of them and then adding them up. Now calculate the power, individual power dissipated by each bulb. Okay, we've already calculated that, but the reason why they didn't put that other question first is because you could have found 37.5 just by multiplying the 2.5 amps times the 15 volts. And then you could do each one by itself. Okay? Finally, consider the circuit below. All the bulbs have resistance R. Okay? So that means they all have the same resistance. Now, what is the resistance of the circuit while the switch is open? Okay, so notice, if that's the case, then it has to go through here, which means everything is in series. So that means that your resistance is just going to be, your equivalent resistance is R plus R, which is 2R. Okay? So your equivalent resistance is 2R. Now, what is the resistance of the circuit when the switch is closed? So now that it's closed, those two are going to be in parallel first. So let's do those first, parallel. It's 1 over R plus 1 over R, which is 2 over R, which means that the parallel one is R over 2. Now let's add the other one. So R over 2 plus R is going to be 3R over 2. So by closing that switch, we've now lowered the resistance to 3R over 2, 3 halves R. So how does closing the switch affect the brightness of bulbs A and B? All right, so let's notice that we want to figure out how that's going to change the brightness, okay? So what we've got is that A is going to have similar current, but doesn't have the same voltage. Okay, so let's say this is going to be voltage V. Okay, we don't know what it is, but what we're going to say then is that we know that voltage V is also going to have current I. Now it turns out that resistor is going to have I, but it turns out that we are looking at two different resistances to begin with. Now, let's say that we started off with 2R. Okay, so that means because we started off with the series resistance of 2R, and we had a voltage of V, then that means that our I is actually going to be, hold on. Our current will be V over 2R. Okay. Now that's going to be our current. That means that the same thing is true up here, is that the current will be V over 2R. But what that means is that the voltage is going to end up being resistance times the current. Okay, so whatever the current was to get started off with. Okay, so we're going to say V over 2R was our current times the resistance is going to equal V over 2. So it turns out that the voltage across the first bulb would end up being half the voltage. Now that means that the other resistor would also be V over, sorry, it would also be half of the voltage. That means that its current would also be V over 2R. So all this is true when the switch is open. Now let's say that we have now closed the circuit, okay? Right? All right. Now we've closed it. Now notice we still had the same voltage to start with, okay? But everything else may change. We now know that the resistance is 3R over 2. What that means is that our current is actually going to be a little bit different. Now our current is actually going to end up being V over 3/2 R, which is going to be 2/3 V over R. Okay, so 2V over 3R. Okay. So we know that the current is going to stay the same for our series component. So that's going to be 2V over 3R right here. Now we know that then, therefore, if the resistance that was there is R, then therefore the voltage over that portion should be 2V over 3R times R, which should be, oops, let me just tweak that a little bit, which should be 2/3 V. Okay. Now let's look at each one of the other voltages. Now we still have 1/3 of the voltage left over each one. So 1/3 of the voltage is here, and 1/3 of the voltage is up here. Now you may be saying, wait a minute, but 2/3 plus 1/3 is the total voltage. Why can you add another third? That's because they're in parallel. So we know the voltages will be the same. Now we also know that this one has a resistance of R, and this one has a resistance of R. So therefore we can now find the current. So the current for the top one, that should end up being 1/3 V over R, which makes V over 3R. Now that's for the current for the top. Okay. Now the current for the bottom one, okay, well, we're going to get the same calculation, which means it's also going to be V over 3R. Okay, so let's make that a little bit clearer. Okay, all right. So what we see is that those are going to have a current. Notice that the current should be the same as 2/3. So 1/3 and 1/3 is 2/3. Now what about the wattage? So how does it affect the bulbs at A and B? Well, for A, we know that the wattage started off as V times I, which was 2/3 voltage times 2/3 V over R. Okay. I have to pause for a second. I just realized I think I got some of these confused. My apologies. Let's fix that. Okay. So let's look at the power on A when we first got started. Now the voltage when we first got started was V over 2. The current when we first got started was V over 2R. So if we use that, that's V squared over 4R. Now our final though is going to end up switching up. Our final was going to be 2/3 V, okay, times the current, which was also 2/3, but V over R. So that's going to give us 4V squared over 9R. So hopefully what you'll notice is that the power ended up increasing. That's interesting. So that's an increase in the power because we closed that circuit. But let's look at B. Let's see what we had. So increased brightness. Okay, there, good. So let's say we had the power of B initially. Okay, so what we're looking at then is when we first get started, we've got across B, the voltage was V over 2, and then the current was V over 2R. So like the other one, it was V squared over 4R. Now though, let's take a look. Our voltage now, once we've closed that circuit, the voltage is going to be 1/3 V, and then the current is V over 3R. So it turns out that it ended up decreasing the power. So decrease in the brightness. Okay. All right. So with that, okay, what we can see is that by closing the circuit, we end up making A brighter, but we ended up making B dimmer. Okay, and that's how we do that. So things to take away. Take note of how it is that we decide equivalent resistance. Then take a look at how we would find voltage and current one step at a time using the properties that we've learned. And then third, we can determine brightness based on power. So as we change our conditions, our power will change and so will the brightness. Thank you very much.